All right, guys. I was going to be at the gym about now, but my wife decided to have a lazy morning. So I figured let's get this done so I can get this to you sooner rather than later so you can start studying or continue your studying, I should say. And you better have already started, right? Okay, so once again, I'm going to go through a number of questions, and along the way, while I'm going over those questions, I should be reviewing um, the concepts as well. So let's zoom in on this first guy here. This first little thing that I've drawn, and just review the concepts, what we're talking about. So we have, on this picture, we have tissue 1, tissue 2. So everything up here is tissue 1, everything down here is tissue 2. Each of these tissues has 2 separate things. I'm going to keep pounding this into your brains because I know some of you are going to have a hard time remembering this. They have impedance values, and they have speed of sound values. Those values are going to give us some different things to worry about. Impedance tells us whether or not we even see anything. It tells us whether or not there is a reflection. Now, Z2 minus Z1, let's see this whole thing squared, Z2 plus Z1. That whole thing is really for only, that equation is only for normal incidence. But that's not to say that I'm sorry, it's a little early in the morning for me to be doing this. It's not to say that just because we're coming in at an oblique angle that impedance doesn't matter. It does, of course, matter. So there's one thing I didn't draw here, and that is a reflection. Let me just put that in. There's always going to be some kind of reflection, and more or less, just do that one more time and make it just a little higher. I think that's exactly the same thing, isn't it? That's okay. So if this angle, this theta incident, theta I is incident, let's say that is, I don't know, we'll just go with 30, I know that's one of the questions anyway, so 30 degrees, then what is this angle? I didn't draw it quite the scale, but that's theta R reflected. What is that angle, guys? Every time it's the same thing. It is going to be equal. Always equal. If I come in at this angle, I'm going to come out at that angle. If I barely graze it, I'm going to graze it. I'm going to come in at a very tight angle, it's going to come back at a very tight angle. So that reflected angle is always equal to the incident angle. Whether or not it reflects, that's a consideration of impedance, Z. Now, whether or not it does this, is a change in speed. If there is no change in speed, you may still have a reflection, but the incident or the continued transmission would be straight, more or less straight, if there was no change in speed, but there was a change in impedance, and that's perfectly possible. Now, impedance being, let's do this, Z. Let's get out of that setting. Density times speed of sound. If the speed of sound goes up, but there's a change in stays the same, but there's a change in density, well, gosh, that would make a change in Z. So there'd be a change in impedance with the different densities, but the same speed of sound. It's possible, perfectly possible. And so if this were changed between tissue 1 and tissue 2, then therefore there would be a change, there'd be a difference between Z1 and Z2, and we would get a reflection. But it would probably be a pretty small change, but because to have a different density and the same speed of sound, it would probably be a small change in density, so only a small percentage, less than 1%, is actually pretty typical. So typically in tissues, from tissue 1 to tissue 2, there is nominal refraction, usually. Sometimes we see it. Sometimes we actually see it, but usually the refraction, if there is any, is so small that we really don't even notice it. Okay, I'm beating on a dead horse. This is how I draw it. This just makes sense for me. But then I took this very same image, I copied it, and I turned it sideways. Now the normal is horizontal, and the tissues, tissue 1 and tissue 2, are side by side. In fact, let's see. Tissue 1. Tissue 2. All right, just kind of as a visual, make sure you're seeing this. We are still going to have reflected angles. That seems about correct. We're still going to have incident. This one was the same amount. Oh, by the way, which speed of sound? So we know, I'm jumping around, aren't I? Try not to do that. We know Z1 and Z2 are not equal because I drew a reflection in there. Probably a very small difference. So maybe 1% reflected and 99% transmitted. We also know that this transmitted, it refracted. So there's a speed of sound change. Okay, so C1 does not equal C2. Tell me, which is faster? Which tissue has a faster speed of sound? I would say C1 is faster, C2 is slower. Theta I is bigger than theta T. That's a sideways T over here. So it slows down. And maybe this looks maybe like a 10% change in speed. which, by the way, is a really large change. So to get that kind of a angle, it requires a pretty decent change in speed. 10% in soft tissue would be a lot. 10% going from soft tissue to bone would be expected, but soft tissue to soft tissue, this at 10%. So let's say it's about 10% slower. Then, this is Kurt's law, right? Then theta t is 10% less than theta I. So whatever theta I was, theta t is about 10% slower. That is just a rule of thumb. It's not a, that doesn't work perfectly, but it's just a rule of thumb. I just did one more thing with this. This is still the same picture, but not only is it sideways now, but I've also flipped it up and down. So we still have tissue 1 and tissue 2. And this is just where, this is the one arrangement where the slow down, speed up picture doesn't quite, and I mentioned this the other day, the picture doesn't quite make sense as far as the mnemonic goes, because this is still slow down, even though my parent angle seemed to go up. Well, it's only up on the picture. It's only up in the way we drew this. It's still, theta t is still smaller than theta I. So slow down still works. Okay, you get that? That's where I wanted to go with that. Okay, so let's look at some of these. So let's see, page 90, number 15. Two media, A and B, have the same densities, okay? Densities are the same. The speed of sound in medium A is 10% higher than in medium B. So speed of sound is different. In A, it is higher. Okay, apparently that's what I just said with the previous example. Which medium has a higher acoustic impedance? But that's not the question I asked before. Which of these has a higher impedance? They both have the same densities, so those are our, I'm just going to put an equal sign there. But let's see, speed of sound in A is 10% higher, so A is greater than B by 10%. So, which one has the higher impedance? Now, if you're hesitating on that, you're not thinking just basic math. This isn't a, you don't even have to worry about the concept here. Obviously, if this number is larger, as in the case of A, then Z will be larger. Okay, so question is, for that question, it is A. Let's see, did I do impedance is important in reflections at boundaries? It's number 16. Oh, number 17. Did I have a... I do number 17. All right, I'm gonna jump down to 17 and then I come back up to that little mess I created up there. So what did I write here? Attenuation. Okay, so the attenuation coefficient in decibels per centimeter. So per centimeter, attenuation coefficient tells you how much is happening every centimeter. whereas attenuation is the sum of all the attenuation coefficients, or the sum of all those centimeters, really. General rule of thumb, and it works pretty well, is in soft tissue, by the way. It works well in soft tissue. Whatever the frequency is, divide that by 2. All right, so, and number 17, we have a 7.5 or a 3.0 or a 3.0 megahertz. So what do we do with that? Those are, to find the attenuation coefficient on both of these, just divide by 2. Gosh, I mean, I don't know. I can't do 7.5. 7.5 divided by 2, 3.75. This turns out to be 3.75. So 3.75 what? Decibels per centimeter. And 3 divided by 2 is just going to be 1.5. Let's see, decibels per centimeter. So, okay. Now you can see why we get concerned about their different frequencies. This guy is attenuating much faster. More than half. Remember 3 decibel rule? 3 decibel rule is half attenuation. 3.75 decibels is more than half of the beam's energy, its intensity, is lost into the body, is lost through heat, reflection, and all that, every centimeter. Whereas over here, considerably less than half. Half of half actually. It would go 2 centimeters before it lost even half of it. But so it could go more than 2 centimeters before it has the same attenuation as this guy over here. So that attenuates much faster. That's a problem. But where is it a problem? Let's jump down to here. Kurt's rule of thumb. Now I have another Kurtism here. Kurt's rule of thumb. Higher frequency is always better until it isn't. So, actually, even though we're attenuating at a much faster rate, the higher frequency is better. In fact, it would always be better until it isn't. Why? When you increase your frequency, you decrease your wavelength, which means your spatial pulse length, which is cycles times wavelength, your spatial pulse length is going to go down, right? Because your wavelength went down, right? Your wavelength went down, and you always, always, always want to measure with the smallest ruler you can get. So if you have an ant, you measure with a small ruler, not a yardstick. So the high frequency is like basically saying a really small ruler. So how are we answering this question? The carotid artery, well, I'm just going to read the answer. The carotid artery is a superficial structure. Since it's a superficial structure, this high attenuation number doesn't matter because we only have to go a few centimeters at all. a 7.5 megahertz transducer is better because a higher frequency transducer produces a better image. So yes, higher frequency transducers produce better images, but they have higher attenuation. So that's the balance point we have. I wanted to go back to here. I had forgotten that I had written some stuff down. I had written some stuff down. Okay, yes, and it says, by the way, not important, but, all right. So I went ahead and I took this linear equation, Z equals rho times C, and I put that into our triangle. And I solved for rho. Okay, so rho then is equal to Z over C. Well, yeah, I mean, mathematically that works. So I did that. I took, and 1.6 million rails is about average for soft tissue. I divided that by the speed of sound in meters per second. And I got 1,038 or 1,039 kilograms per meter cubed, which is about to say 2,290 pounds per meter cubed. I went to a website to find the conversion on that. This seems about right. So what does that mean? If I took a 3 foot by 3 foot by 3 foot square of human flesh, sounds kind of gross, but if you think about 3 foot, that's not very tall, but 3 foot wide, 3 foot deep, that's actually a lot of meat. That's a lot of liver and fat and whatever. If you pack that all together, 2,290 pounds seems about right. So this is totally unnecessary, but it just kind of, it makes you, because the reason I did this originally, I did this, I think 1 or 2 classes ago, because I really wanted to, I'm like, where did they get rho? And how do they come up with rho, or how do they come up with well, the rails are completely different. So I went ahead and solved for rho, and I'm like, oh yeah, that seems about the right density for a cubic meter of human flesh. Anyway, totally unnecessary, so erase that from your brain. And you probably want to erase the image from your brain anyway. Okay, so moving right along. Okay, page 96. Questions 1 and 2. Question 1, page 96. A pulse of ultrasound is propagating in soft tissue, such as liver. The pulse strikes a boundary with a different soft tissue at normal incidence. What portion of the intensity is reflected back toward the transducer, and why? Doesn't really give us a whole lot of information, but we can make some assumptions here. We are just talking about tissue 1, which is, well, it's just liver, and tissue 2, we'll call it a lipoma. I don't know, or some kind of fatty tumor, let's say. Soft tissue to soft tissue interfaces always produce actually surprisingly small echoes. Usually it says about 1%, right? Yeah. Usually less than 1% between liver and fat, liver and muscle, or so. Usually about 1% is reflected, which means 99% is transmitted. And that's pretty much the answer. The impedance of soft tissue. So the impedances of soft tissues are similar, and the difference in impedance directly determines the intensity of reflection. So if the impedance was fairly high, then maybe 5% would be reflected. if the impedance difference, I'm sorry, the impedance difference was fairly high, 5%. If the impedance difference was quite high or very high, then maybe 50% or 75% is reflected. At that point, you're not really seeing anything. What we have in that case, what we have is a shadow. Here, let me draw a couple of new arrows here just so I can, so if this guy came down like this, and then there's a reflection of 75%. So basically I'm drawing, of course this is 100% because it's 100% of whatever that is, whatever the incident intensity is. And then this is 75%. And only 25, because remember these all have to equal the original, the reflected and the transmitted have to equal the original incident. So 100%, 75% reflected, 25%. That ain't much. 25% going through is not much, and 75 reflected is a lot. So you'd have a shadow, and this interface would be very echogenic. All right. Let's see, I have question 2 here as well. Sound is traveling in a medium and strikes a boundary with normal incidence. Okay, so we'll use the same picture, I think. If 63% of the wave's intensity is reflected back toward the transducer, what percentage is transmitted? Well, okay. So let's just change our numbers. It's the same thing as I basically just said. If 63% is reflected, that means we subtract that from 100 and find it's 37% is transmitted. Okay, I guess this is number, I have a little picture of a bone down here. That must be, oh yeah, it is number 3. Okay, so this is something I just want to reiterate. Sound is more than, even though sound reflects off of bone, it is more than happy to travel through bone. It is, even though sound reflects off the surface of water, whether you're in the water making noise or outside the water making noise, the sound is more than happy to travel. Sound stays in the impedance that it is currently in. So if sound is produced in bone, well, that's all well and good, but it will actually stay in the bone, mostly. I mean, obviously, some of it's going to come out, leak out in places, but if it starts in soft tissue, it tends to stay in soft tissue. If it starts in air, it tends to stay in the air. It stays in its own impedance. It cannot jump impedance, as we see right here. It doesn't really like going into a different tissue if the impedance is very large. And this is at normal incidence. If you come in at an angle, probably, I don't know the mathematics, because it does change, probably rather than 63%, it's probably closer to 100%, and very little goes through. So sound stays in the impedance layer that it is created in. So, okay, number 3, a pulse of ultrasound is propagating in bone, which is weird. I don't know how it got there in the first place, but we'll take it, and strikes an interface with soft tissue at 90 degrees. In other words, normal. A giant reflection is created. Yes, from these facts alone, what can be said about the impedance of bone? What can be said about the impedance of soft tissue? Well, we could say, because of the large reflection, we could say those impedances are different, but we don't really know we don't really know what the impedance is. We don't have any numbers. What can be said about the differences between the impedances of bone? Well, I just answered that last one. Okay, answer. Nothing can be stated about the impedance of bone or soft tissue based on the information given. Right, but we can't. So the only thing we do know is that this very large reflection here so that's going the other direction. And let's just say for the fun of it, it was a 99% reflection, which means tiny little bit, 1% made it out of the bone. So a large difference between Z1 and Z2. That's all we're concerned about. Reflection, Z1 and Z2. Speed of sound is very different, but we're not concerned about that right now. It's it's not asking the question. And B, even if it did ask the question about refraction, there would be no refraction. Why? Ooh, that might be the next question. I think it is the next question, so I'm not going to answer that. I'm not going to answer that. Is that 104? On page 104, I have some, gosh, this tiny little picture is supposed to handle a whole bunch of questions. I might have to, well, okay. Okay, so just for the fun of it, in fact, let me pause this. I'm gonna make this picture bigger. Okay, so made it a little bit bigger. Let's see, a pulse of ultrasound propagates in soft tissue such as liver. Pulse strikes soft tissue interface with an oblique incidence. Anything other than 90, oblique. Some of the sound energy is transmitted. To what extent is the transmitted beam refracted? Well, so just for the fun of it, guys, I just made tissue 1 at an angle here. So that's the only reason why it's drawn like this. So just for the fun of it, there's tissue 1. Tissue 2, okay. And let's see, it said some of the pulse strikes, some of the sound energy is transmitted. To what extent is the transmitted beam refracted? Well, I guess they're not really giving us numbers, are they? So, and they're not saying anything about the speed of sound. So we're going to have to assume a identical speed of sound. So no refraction, C1 is equal to C2. But there is a reflection. So let's see, I'm going to hold this thing sideways so I can get this angle somewhat correct. Okay. So there was a refraction. I'm sorry, a reflection. So, boy, this looks funny when we draw it. We kind of draw this little cockeyed, but I want to show you that it's not always going to be perfect for you. And what could we say? Well, if this is 100%, and it said some, well, some, that doesn't sound like much. Let's say 25% went through, then 75%. And these numbers obviously are made up because they didn't give us any numbers. Answer, the transmitted beam undergoes little to no refraction. Well, okay, little or no refraction, which is actually what I drew, but that's just, okay, because typically the speed of sound doesn't change that much, so that's okay. Transmitted beam is refracted when the incidence is oblique and the propagation speeds are different, but because the tissues on either side of the boundary are both soft tissues, their speeds are nearly identical and there's no, oh, I thought I asked something about reflection. Some of the sound is transmitted. To what extent? Oh, at what extent is it being refracted? I didn't read the answer. I didn't read the question correctly, but I accidentally got the answer correct. Because, so it's really all it's asking about is refraction. So, apparently there's a sidewalk sale. Okay, let's just draw the normal in. How would I do that? So normal would be, so that would be the incident angle. And here is the transmitted angle. And I drew them almost perfectly the same. So refraction is very, very little, if at all. So I totally screwed that one up. Shoot, I think I wanted to use the same picture though, multiple times. A sound pulse travels in medium 1, this is number 2, strikes an interface with another tissue, medium 2, at 30 degrees. The angle of transmission is 10 degrees. From these facts, well, I'm an idiot. All right, let me pause this. I need my picture back. Okay, so I'm still using this funky picture where everything's a little bit off kilter. I'm doing that on purpose to kind of shake you out of just accepting everything as perpendicular or horizontal, and there's only 2 ways of looking at things. And they're just kind of shaking it up a little bit. Not exactly like going crazy or anything, but what do we say? I think he said the incident angle was 30 degrees. So theta I is 30 degrees. And here's the normal, and the theta transmitted was only 10 degrees. Right? Let's see. Medium, maybe 30-degree angle, the angle transmission is 10 degrees. From these facts alone, what can we say about the speed of sound in medium 1, speed of sound in medium 2? Well, okay, so far, medium 1 or tissue 1, tissue 2, we know the speed of sound is different because there is a significant refraction, which is faster. So what happened to this? Did it speed up or slow down? Seems to have slowed down. So it looks like C1 is greater than C, greater than, it's greater than C2. The difference between speeds, okay, let's see. Answers. Given only this information, we can say nothing about the speed of sound. Yeah, and I didn't. That's a C. That's a greater than. Yeah, we don't know what the speeds actually are. We just know that there is a difference. There's a significant difference. And the speed of sound has got to be faster in 1 than it is in 2. We could say perhaps that this is liver and this is fat. I don't think the change in speed is that great, but there is pretty significant, and so that does cause some problems. Okay, let's see, I think I wanted number 3. A sound pulse travels in medium 1 and strikes an interface with another tissue, medium 2, at 30 degrees. The angle of transmission is 10, so far the same thing. In which medium does sound travel slowest? Well, we already determined that. That's second medium. 4, sound, once again, strikes the interface at 30 degrees, the angle of transmission 10. In which medium is the impedance higher? Ooh, is Z1 and Z2. Remember, so we do have a reflection here. At least I've drawn in a reflection anyway. So which is higher, Z1 or Z2? We don't know. We don't know. Z is equal to density times speed of sound. Well, we know the speed of sound is higher in medium 1, but we don't know anything about the densities of these two. And so the density could be significantly less in medium 1 as well, which would make the impedance, let's see, smaller in 1. So without really knowing what's going on with density, how could we say what the medium or what the impedance is in either one of those? Number 5, sound travels in a medium and orthogonally. Orthogonally. Well, what? Right. Orthogonal, right? Just same thing is oblique, really. No. Idiot. 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 I am so sorry. I said that wrong, and that just goes to show that, well, I'm an idiot. That's what it goes to show. It's orthogonal. Orthogonal is the same as normal, is the same as 90 degrees. Anyway, sound travels in a medium orthogonally. It strikes a boundary with a different medium. Although sound waves traveling in the medium have very vastly different speeds, there is no refraction. What kind of answers the question? It kind of answers the question, but I mean, so it on normal incidence here, let me just borrow this picture here. Well, think of it this way. Kurt's rule says when you come in and the speed of sound, like here, the speed of sound is different by 10%. Let's say it slows down. Let's just say here that medium 2 is 10% slower. You'll have about a 10% reduction in angle. That's Kurt's law. But what would be a 10% reduction in angle 0? If your angle is 0 degrees, what's 10% less than that? What's 10% more than that? If your base is 0, it's 0. And so that's mathematically the way to look at it. So even though the speed of sound is considerably less in medium 2, there is no refraction. Okay. Okay, well, if you didn't notice, I paused you there for a second. Let me just read through number 7 here on page 105. The impedance of medium 1 is 8 rails. I'm sorry, I'm leaning up against the table there. The propagation speed is 1450 meters per second. The impedance of medium 2 is 6 rails. By the way, that's a pretty significant difference in rails. And speed is 1.855 kilometers per second. Oh, really? A sound beam strikes the boundary between the media and is both partially transmitted and reflected. The angle of the incident beam is 30 degrees. What is the reflection angle? Okay, so your BS meters should be going off right now. We do care that there's an impedance difference, but the fact that they gave us 8 rails and 6 rails and a propagation speed of 1450 meters per second and then a 1.855 kilometers per second, all of that is extraneous information. It is designed to mess with you. It really tests whether or not how well you know this, because the only thing that we care about is that the angle of the incident beam is 30. The reflected angle, therefore, is 30. It's going to be the same, always the same reflected angle. Okay, oh, page 106. Oh, page 106. I drew the little picture they have here, more or less. I think I could add some numbers here. So there's mediums 1, 2, 3, and 4. We have 1.5. Let me get a better pen. .5 rails, 1450 meters per second, which is our standard speed, even though it's in meters per second. 3.5 decibels per centimeter. So what is that? That is our attenuation coefficient, not attenuation. Attenuation would be every centimeter added together. That's the coefficient, and it's fairly high, right? So, okay, so they use the same all the way across. Let's just go to 3.5 decibels per centimeter. 3.5 decibels per centimeter. And ta-da! Okay. So let's just go through these 9 questions on page 106. I think it's a pretty good compilation. Okay. Number 1, what does the, well, I didn't write that down. 100 milliwatts per centimeter squared. What does the 100 milliwatts per centimeter squared represent? It represents, of course, the incident intensity. What does 3.5 decibel per centimeter represent? Well, I guess I kind of already told you that. So every one of these has the same attenuation coefficient. So attenuation coefficient is generally found by frequency divided by 2. Well, that kind of makes sense that these are all the same attenuation coefficient because only one frequency is going in. In fact, what is that frequency? So what is that frequency? It's 3.5 decibels per centimeter. Basically, we just do 2 times 3.5 is 7 megahertz. Well, that doesn't, it's 7 megahertz. This is 7 megahertz. I don't know why I drew it over there. Equals, let's just erase this now. That's what equals 3.5 decibels per centimeter. Okay, so that's your attenuation coefficient. 3, if the media are soft tissue, what is the estimate of the ultrasound frequency? Oh, okay, we just did that. 7. What property has units of Rayles? How is it determined? What property has units of Rayles? Well, what they're asking, what property is really, what are Rayles units for? Impedance. So, and how is that determined, I think is the second part. Yes. Density And that's actually in kilograms per centimeter cubed. Oh gosh. No, I can't. Is it centimeter cubed or meter cubed? Stupid me, I can't honestly remember. Kilograms per meter cubed. Yeah, sorry. That makes more sense. Oh, duh, how would I not know that, guys? We just talked about how I drew that box that was a meter cubed. See? Just because I'm your instructor doesn't mean I'm thinking. Oh gosh, what page are we on? Lost on the page. Well, anyway, while I'm still looking for this page, page 106. What was it? Oh, C, speed of sound. And that would be the meters per second would be the easiest one because you're dealing with meters over here. Okay, so that's how it's found, density times speed of sound. 5, the incidence between the sound wave and boundary between 1 and 2 is normal. Yep, 1 and 2 is normal. What happens at the boundary between media 1 and 2? Okay, what happens at the boundary? Well, at this boundary then, what can we say happens here? Well, there's transmission. Let's see, 1.5 rails and 0.5 rails. Why does that matter? Because that determines whether or not there is reflection. There's a pretty significant change in impedance, so there's going to be reflection. So there's going to be incident, transmitted, reflected. But what are we not going to have? We are not going to have refraction. Number 6, the incidence between the sound wave at the boundary between 2 and 3 is normal. Yeah. What happens at the boundary between 2 and 3 and why? Let's see. 0.5 rails and 0.5 rails. This boundary, as far as we are concerned, is invisible, doesn't exist as far as we know. Sound travels through and no sound is reflected at the boundary. How did you do that? Okay. Oh, that was 16. Transmission only, the impedance is the same. 7, what type of incidence is there between 3 and 4? Oblique, yes. See, right here is an oblique angle. What happens at the boundary? And what happens at the boundary between 3 and 4? Okay, well, there will be reflection. (1450), 1540, and there will be refraction. Now let's think about this. Speed up. Let's see. Normal is here, so speed up. The refraction would be like so. So it'd be let's just erase everything here. And zoom in. Honey, I'll be ready in just a second to go to the gym. Okay, so incident reflected because of the rails. We know there's reflection, and it speeds up. And so since the normal is here, it's going to speed up like that. In other words, this angle is greater than this angle. Okay. Number 9, what processes occur as the ultrasound passes through all media? Well, let's see. Well, there's attenuation, so all reflection, scattering, and I chose this media on purpose, this coloration on purpose. Remember, there's all sorts of stuff going on, all sorts of crazy things going on. It's not as simple as we normally draw it. What are the units of this process? So if we're talking about attenuation, the attenuation coefficient is decibels per centimeter, but attenuation is decibels because it's all the centimeters. It's kind of a, so decibels. And yeah, looks like I got that correct as well. Oh, actually, this is really good timing. My wife has dragged herself out of bed. And we actually just finished up the last question I wanted to get to. So hopefully this is good, guys. If you have any questions, let me know. And that is it. Adios.